Morning, ladies and gentlemen. I know that there's still a few people to join us. We've a very busy schedule this morning, so I won't hang about. Just to say thank you very much for joining us here this morning on what is a very important webinar for us. It's one of the last in a series as we come towards the end of EU-SysFlex. We will be hosting a final event next month on the 7th. And there are actually a further workshop on demonstration projects later in February. So anyway, I won't delay. Soon I'll introduce our speakers, however, just to ensure the best possible experience of the material. Everybody's going to leave their cameras off while they're presenting. And if you could do the same yourself and make sure you're muted, that would be very helpful. We really want this to be a bit of an interactive session, so please do use the chat facility to ask your questions. And at the end of each session, we will try to get to the questions. We'll also have a small poll as well, which we're going to use Slido. You'll see at the top of your screen there in Teams, beside the little hand wave is an S. And that, if you click on that, that will activate Slido for you to enter your answers for the poll. So the agenda and speakers, maybe we'll move on to the next slide then. So just to introduce our speakers, they might turn on their cameras. So we have Marianne Evans, who's the technical manager of EU-SysFlex and is with EDF. And Marianne will give an overview of the scarcities identified in the power system and the mitigation flexibilities tested in the EU-SysFlex project. Marianne will also, at the end of the session, summarise our key findings on flexibilities of the power system. Yi Wang and Gregoire Prime of EDF are our research engineers, will present on inertia and frequency stability mitigations for continental Europe. This will be followed by our colleague from PSC and Matthias Swartsky, who's a power system analyst with PSE on voltage and rotor angle stability mitigations for continental Europe. And then my own colleague, David Corcoran from EirGrid, who's a senior lead engineer, will present on frequency and voltage stability mitigations and congestion management for the island of Ireland. And then the last of the primary technical presentations will be given by Caroline Bono from EDF, who's a senior engineer on support balancing with new flexibilities for large share of variable renewables or variable res integration in Europe. Okay, we'll move on. So there's everybody just to say hello, all our presenters.
Good morning.
Good morning. Morning, everybody.
Good morning, everybody.
We'll move on to the next slide. We're slightly behind schedule. So just to give you a very quick overview of the EU-SysFlex project, very large European funded project. It's been ongoing for over 4 years now. We're coming towards the end of it now in February. It's a budget of 26.5 million, supported by Europe at the tune of 20.5 million. 34 organisations across Europe, 12 work packages, 7 demonstration projects, and over 100 deliverables. So we're coming towards the end of that 100, submitting all of those 100 deliverables. So we move on. And just to provide a little bit of, just to give you further information on our consortium, it's made up of TSOs, DSOs, technology providers, research institutes, and so on. Okay, we move on. This slide is just to provide a little context of the primary focus of what EU-SysFlex is really about. And it's all about the ability to integrate non-synchronous technology out to 2030. So we will see how the generation mix looks today and how it will look in 2030. And there is a significant increase in reliance on non-synchronous technology such as wind and solar. And from a system operation perspective, EU-SysFlex is all about trying to create and identify solutions to help us integrate and utilize that capability on the European power system to the greatest extent. We move on. Obviously, there's additional complexities in the system that we are all aware of, like the electrification of transport, heat and cooling. There'll be less inertia on the system due to displacement of traditional thermal power plant with the increase of renewable technology, congestion on the system, increased demand, a shift in dynamics from a centralized system to a decentralized system, further integration or further interconnection, large-scale deployment of grid storage, interconnection, and then obviously the hot topic of the moment is hydrogen. So we move on. So the dimensions of the project, and we're going to focus on today is system scarcities and the characterization of technical scarcities. We looked at the market and regulatory dimensions in terms of the augmentations that are required to incentivize the right investment in flexibility on the power system. Through demonstration projects and trials, was the identification of flexible capability of technology to deliver system services to the European power grid. And then support tools, so system operator development and identification of the need for system operation tools to support operating in a high-level environment. And then finally, ensure scalability and replicability of our solutions. So move on. This is just to summarize work package 2. As I said, 12 work packages. This is probably the largest work package in terms of the analysis that was carried out. We've held a series of webinars on elements of this work package, which you can find on our website. They're very interesting and informative webinars, so please do look at them at your leisure. And then obviously today is the final one from work package 2, which is the mitigation of the technical scarcity associated with high levels of renewables on the European power system. And without further ado, I will introduce the technical manager of EU-SysFlex, who works for EDF in France, Marianne Evans. I'll hand over to you, Marianne.
Thank you, John. Good morning, everyone. So I will introduce briefly this webinar. I'm very happy to welcome you all to this final webinar of Work Package 2. So if you can move to the next slide, please. So as John was explaining, and you can see it on the right-hand side, you see a figure illustrating all the different tasks and activities that we carried out in the EU-SysFlex project. And the big responsibility and objectives of Work Package 2 was to try and quantify and support the scarcities that we had already identified in bibliography, but that we wanted to support and quantify with models and simulations. So it's the green box here in the middle of the figure, which was in charge of doing all these simulations. So in order to do that, and we were several partners at European level to be involved, quite strongly involved in this work package, we developed 2 core scenarios that were like the skeleton of our work to, let's say, to share together the contexts of progressing towards higher shares of renewable energy sources. So electrical renewable energy sources. So the 2 core scenarios are both building, the way to net zero and progressing towards decarbonation. The first scenario called energy Sorry. Can you mute yourself, please? Yeah, thank you. So the first scenario is energy transition.
Hello. We lost Marianne.
Hello.
We can hear you now, Marianne.
Yeah, I think I was muted when we muted the attendance. Can you hear me now?
Can hear you now, yeah.
Okay. So I was just introducing the 2 core scenarios that we shared between partners So both ambitious in terms of res targets for 2030. So one with 52% res and the second one with 66% res. And as you can see here on the graph, with a percentage of this is increasingly from wind and solar, so variable res generation. So displacing, let's say, conventional, traditional synchronous machines, plants that were historically providing the flexibilities and the services to the system, and transitioning to variable res. So the share of variable res is over 35% for the renewable ambition scenario. And these res are not only variable, but they are non-synchronous, and they're also decentralized, so they're not located in the same places of the system as the conventional plants. So this is creating scarcities. If you can move to the second slide, please. And those scarcities have been identified in the previous tasks of Work Package 2. So it was the webinar that we held in June last year. And with the two core scenarios and sensitivities that we built, and my colleagues are going to present them to you in a bit in more details just afterwards. We identified the scarcities not only in the continental system for Europe, but also for the Nordic system and the island of Ireland. So as you can see here, you have a summary of what we obtain in terms of simulation results in 2.4, and that confirmed that we had scarcities appearing in the system, not only in balancing, but also in frequency control and also in congestion management. I just wanted to underline that in blue, it's not no scarcity. It's just that in our scenarios and with the parameters that we used, we didn't see it with our simulation. But it doesn't mean that there won't be any scarcity. And just to summarize, what you can see is that in reds, some scarcities are already there in the systems, but a lot of them are already concerns or evolving characteristics in the other systems, even what are considered strongest systems like the continental European system. So what we did in this task and what we're going to present today, last slide, please. Yeah. Is we integrated some solutions. We proposed different solutions, and we observed by simulation in the system the mitigation of the scarcities that we had identified in the previous tasks. And this is what we are going to present today. Sorry, I have the box in front of my slides. Yeah, thank you. So we're going to see this proposed solution. So some solutions that we tested at EDF to mitigate the lack of inertia, but also at AirGrid as well, synchronous inertial response. Then AirGrid is going to present some work that they have been doing on mitigation to contain frequency. Then PSE and AirGrid are going to present their works on voltage stability control. Then PSE will present some of the work that they have been doing on oscillation damping, and also with AirGrid on rotor angle stability, and some mitigation of the stability issues that we had seen in the previous works. And then finally, AirGrid is going to present some mitigations that they have tested on congestion management, and EDF to maintain system balancing and adequacy using flexibility solutions such as batteries and electric vehicles. So I will now give the floor to, I think it's, my colleagues Grégoire Régnier to present the work of EDF on inertia.
Thanks, Marianne. Just to be aware, we're just slightly behind time, so if we can push it on a bit, that would be appreciated.
Okay. Thank you, John. Thank you, Marianne. So I will start. You can hear me clearly?
Yes.
Okay. So our study focused on assessing the inertia need and cost facing system splits in the future continental European power system. So you can move on to the next slide. I will just introduce the problematic. As you might know, the inertia of the European power system is decreasing due to the increasing penetration of non-synchronous renewable generation and the decommissioning of conventional power plants. On the other hand, interconnectors' capacities will need to be reinforced in order to better deal with the variability of wind and solar at the European level. The increase in power exchanges and the reduction in inertia would consequently cause high rate of change of frequency, or the so-called runoff, in case of system splits. Critical thresholds may be exceeded, and defense mechanisms such as load shedding could be, in some cases, insufficient or too slow to react, leading to generators disconnections and even blackouts.
Okay.
This scarcity related to frequency stability has been assessed in detail by EDF. In the previous, sorry, somebody can mute himself. So I would just continue. You can hear me?
Yes, yeah.
Okay. So this study related to frequency stability has been assessed in detail by EDF in the previous task of work package 2 through dynamic simulations using our Paladin platform. So Paladin models the continental Europe in 5 interconnected zones: France, Italy, Iberian Peninsula, northern and eastern zones, as you can see on the figure, and can be used to simulate the dynamic frequency behavior of each zone when it is fed by a unit commitment and economic dispatch model called continental. For each hour of the year, 3 configurations of system splits were simulated: the separations of Iberian Peninsula and Italy from the rest of Europe, as well as the split of Europe in 3. All 3 events considered correspond to what happened similarly in real life. You can move on, you can click on the, yeah, thank you. So detailed results of our assessment can be found in deliverable 2.4 published online. And it was generally observed that high rock values were reached in almost all the split configurations. As shown in table, for the renewable ambition scenario with 66% of renewables in Europe, runoff higher than 1 Hertz per second were observed in many hours, especially for both the peninsula's splits. Therefore, we continued our work within task 2.6 to propose some mitigation actions and try to assess them from a technical and economic perspective. That's the topic of today. Now, I will hand over to my colleague Grégoire to present you the methodology applied and the main findings of our study.
Okay, thank you very much, Ye. So I'm going first to describe very shortly the methodology we developed and we ran to achieve this study. And basically what we did was introduce within our model Continental some new constraints called inertial constraints, which are basically derived from the Rokoff equation. I think you all know that formula. And with these constraints, first we applied it in each zone prone to be separated from the rest of Europe. And each one of these constraints, let's say, force Continental to put enough kinetic energy or enough inertia. It's the same thing. So enough kinetic energy so that in case of grid separation from the rest of Europe, the big imbalance caused by the interruption of interconnect flows would not entail very high Rokoff. For instance, Rokoff max could be set to 1 or 2 Hertz per second. So if we apply this constraint, for instance, in the case of the Iberian Peninsula, as we did, that means at any times, Continental has to decrease a little bit the interconnect flows, or maybe has to put more conventional units in order to increase the level of inertia. So by these 2 actions, we're going to secure the system in case of grid separations. But obviously, these two actions will have some consequences in terms of cost plans, so financial consequences. Okay, next slide, please. And still on the methodological part, we also develop another tool which is called Synchronous investment loop, whose goal is to assess the optimal capacity for each vulnerable zones of synchronous condenser. So how does it work? It works hand in hand with Continental by iterations. First, there is a first run of Continental. It's possible then to extract output from Continental and to use them to generate some economic criterion in order to know if we have to invest or not synchronous condenser in each vulnerable zones. And if it is the case, so that new synchronous condenser are installed in specific zones and are put in the data set of input data of Continental, and then we can rerun Continental and so on and so forth. And after 100 iterations, we're going to have the optimal synchronous condenser fleets across Europe. So here is the basics of the methodology. We can now move to the next slide, please. Okay, so just to focus on the main assumptions. First, we implemented 8 local inertial constraints to model the 4 splits configurations. For instance, in France, we had to put 3 split configurations, 3 local kinetic energy constraints, because France can face 3 split configurations. Another very important parameter was the max operational work-off. So we chose as the reference value 1 Hz per second upon ancillary recommendation, and we also tried to, with 2 Hz per second, let's say, as an optimistic vision of system resilience. Okay, and third, we also needed technical features, and we also need to make some assumptions about synchronous cost, investment and maintenance cost. And hopefully we found some relevant information in a Terna theory paper, which was released 3 years ago. So with these assumptions, we can move to the next slide. We then were able to run the simulation and to achieve the studies. And the first results were the investment in synchronous condensers, which are summed up in this table. So you can see that in the first columns, we have the case 1 Hz per second case. And basically, the model invested an amount of 100 GVA of synchronous condensers, mostly concentrated in both peninsulas, in Iberian Peninsula and Italy, and a little bit also in France and in Germany and neighbors, and no synchronous condenser in Eastern countries. Obviously, in the case 2 Hz per second, because it's a most optimistic vision of the system resilience against a very high work-off, then the need for synchronous condenser is lower and only concentrated in the peninsulas. And another information interesting in that slide is that you can see that the synchronous condenser are largely used across the year, several thousand hours a year, and we also have a specific example of some Spanish synchronous condenser, which run more than half the year. Okay, if we move to the next slide, please. Okay, now are the results in terms of system implications with annual total for several values: interconnector flows, cut payments, CO2 emissions, and total production cost. All these values are a deviation from the reference case, and the reference case is a case with no kinetic energy constraints, so there are no constraints of this kind. And we can see that in the case 1 Hz per second, we have a slight decrease of interconnector flows, -6%. So because we cannot export as much as we did at the beginning, we have sometimes to curtail the reads. plus 2%. That generates some CO2 emission plus 1%. And globally, the total production cost increased by around 2 billion euro a year. Half of this amount relates to the fixed cost of synchronous condensers. 10% of that amount is for the synchronous condenser losses. A quarter of this amount is because of less optimum use of the interconnectors. And finally, something very interesting is on the chart on the right, it's a purple area, which represents additional failure. And it's important to realize that because of the kinetic energy constraints, we cannot import as much power as we need, and that could trigger sometimes some supply shortage, additional failure, and especially, of course, during a period of very high consumptions. And if now we move to the next slide, please, we tried to answer the question: what will happen in case of no synchronous compensators installed? So we ran the same simulation without any synchronous condensers, and all the results are in the second column of the table. And basically, in a few words, all indicators worsened, and it's especially the case for the last one, which is the total production cost, because we have now more than 20 billion euro of extra cost. And if you look at the chart on the right, you can see that most of the costs are coming from extreme high new load failure, load shedding because of power inadequacy, because we cannot import as much as we require. And it especially happens in Italy. Okay, if now we move to the...
Just taking the time.
Okay, yeah, of course. Okay, so just to finish, we have here a visual effect of what I've just said about the impact of kinetic energy constraints. We are just going to look at the first chart, which displays the duration curve for the import-export of Italy. So the blue curve is a curve for the reference case, and the red curve is a curve when we activated the kinetic energy constraints. So you can see that we cannot import as much as we did in the reference case, and that explains why we have so much power shortage. And we cannot also, on the left part of the graph, we cannot export as much as we did, and that explains why we have some risk curtailment. And the good news is that when we install synchronous condenser in Italy, we can restore the interconnect flows to, let's say, similar values as in the reference case. And I think I'm now going to give the floor to Ye, so that you can finish and conclude.
Okay, I'll try to do it quickly.
Yeah.
So as the final step of the methodology, as mentioned by Gregor, manifold verification, the frequencies in each zone following the predefined grid splits were simulated using Paladin. The table to the left sums up the results, and it is clearly shown that inertial constraints implemented within Continental are sufficient to ensure the power system resilience in case of grid splits. As an example, the figure to the right illustrates the monotonic function of the record values in the Iberian Peninsula zone following the splits, assessed over each 500 millisecond period for different cases. As can be seen, Rakoff can reach more than 10 hertz per second without inertial constraint, so which is not manageable by system operators in practice, but remain under 1 hertz per second with the help of the implemented inertial constraints and additional synchronous condensers. So we can move on, please. So just to conclude, for the future power system operation, it is essential to assess inertial level and to consider it seriously in order to ensure system resilience in case of grid splits, it is possible to secure the European power system by limiting the interconnectors flows. However, this will significantly increase the system costs and cause extra renewable generation curtailment and the CO2 emissions, as you can see from the results that were presented. Therefore, we propose and calibrated a complete methodology based on continental and Paladin models to assess the optimal mix of mitigations. The results clearly highlighted the technical economic interests for investing in dedicated assets to provide inherent inertia, such as synchronous condensers. Its effectiveness for ensuring frequency stability was proven also by simulations. You can move on, please. And just to complete the conclusions, several points could be further discussed. As the topic of electrical system stability is quite vast. For example, it would be of good value to consider other split configurations, like internal splits in Germany or in France, which could also occur in reality. Note also that grid splits are very complex instance, so it would be good to also perform studies with proper electromagnetic tools and with detailed grid modeling. That would be helpful. Another point is that we only consider the capability of synchronous condensers to provide inertia, but have not assessed other promising solutions such as grid forming controllers. So it could be good to assess them and to compare. And last but not least, it is very important to address other stability issues such as voltage regulation or short circuit power to have a broader perspective of stability issues. For example, it would be very useful to assess the potential of synchronous condensers to resolve also these problems. So, okay, I think I was a little bit at the end, but if you have any questions, I will be pleased to answer, and we can further discuss on that.
Okay, thank you very much, Yi and Gregor, for a very interesting presentation. We are a little bit behind time, so we'll try and get through it. Just looking at the chat, and as we said, please do use the chat for questions, and we'll try and get to them. I think the primary one to date has really been about availability of the slides and the webinar, so it'll all be available on our website for you to review in detail and spend more time on it. We'll move very quickly to one quick question on Slido, I think, just to get a sense of your view. So you'll see that there's a Slido link at the top of your page. It's the S button just on the bar. You'll see it at the top. So if you click on that, it will open up Slido. And the first question being, among the solutions, which one, the below solutions, which one do you think is the most relevant to be implemented in the future power system for ensuring frequency stability? So minimum amount of inertia provided by must-run conventional generators, reduction of interconnector flows, synchronous condensers with or without flywheels, and batteries and inverter-based variable generators with grid forming capability. So if you could just select what you think is the most relevant in your opinion. We'll give it 30 seconds. Okay, so we've approximately 80 people attending. We've 19, 20 live polls. So please do use the facility. And in the meantime, if anybody had a question, one question maybe, if you want to raise your hand, I'm going to ask the question and then get back to our presentations. Okay, look, we'll move on. It would seem that most people believe that batteries and inverter-based variable generators with grid forming capability are the most likely. Yi, do you have any comment or Gregor on that outcome of the poll, very briefly?
Yes, that's interesting because, of course, grid forming will be a very good option in the future, and we have to invest on it. And the second solutions of the poll is synchronous condenser. So I think I agree with that. In our methodology, we couldn't take consideration of the batteries with grid forming capability because it was too complex to implement. And additionally, battery are multi-service assets. I think they won't just supply inertia, and it wouldn't make sense to just commission battery just for grid farming and aspect and inertia. So to take into account batteries, we would have to develop a broader methodology. It would have been more complex, and moreover, we lacked also economic data for grid farming, and it was easier to do it with synchronous condenser. And but maybe in the future we could do another steps on it.
Yeah, just a quick comments on that also. Yeah, I agree with what Greg said, and it should be noted also that at this stage there is still little information, public information about the cost of the grid farming assets, and the large deployment of this technique is still to be demonstrated. So considering that, we haven't assessed the grid farming technologies in our study, but it will be interesting to do that in future when more information will be available.
Further projects, right? Okay.
That's the one.
We'll move on now to the next presentation, and I'll introduce our colleague from PSE, Mateusz Swartzky, on voltage and rotor angle stability mitigations for continental Europe. Floor is yours.
Good morning, everyone. Once again, thank you, John, for introducing me. So I would be grateful if you could confirm that you can hear me properly.
Yes, we can hear you.
Okay. Okay, thank you. So I move on. We are running out of time, so I will focus on the voltage stability issues as it is more broad subject in our presentation. So I would like to present you the key results and conclusion regarding technical scarcities that we have identified in task 2.4 of the SysFlex project, and then their mitigations according to the voltage stability for continental Europe power system model. So in the first step, I would like to introduce you into the results of what we have achieved in the task 2.4. This task was focused, as it was previously mentioned, on identifying the technical shortfalls, scarcities for pan-European system, or focused on high levels of renewable generation. So regarding the steady state voltage control, we have performed several types of technical calculations, including load flow calculation, PV and QV analysis focused on identifying a steady state reactive power stability scarcities, and also we have identified short circuit analysis what we have focused on the system strength, which is also in conjunction with the power system voltage stability. So we have performed our analysis for the three capacity scenarios, which have been considered both in the voltage stability and also the transient ones for continental Europe power system model. So the first scenario was the core EU-SysFlex scenario energy transition that has been presented by Marianne in the beginning of our presentation. Then in PSE, we have developed the two network sensitivities for the purposes of our work that have been taken into account. And next slide, please. Could you click 2 times? Okay, thank you very much. The first network sensitivity is going green, and it's this scenario assumes that even more than energy transition, renewable generation, including wind and PV, is installed in Poland, mainly to the extra high voltage and high voltage grid. And could you move on to the next slide? And click 2 times, please. Okay, great. And the second version of this scenario is the distributed renewables scenario. It assumes the same amount of the renewables connected to the Polish power system, but the general assumption for this scenario is that some renewables are moved to the radial distribution system in the middle voltage and low voltage network equivalents. So that's the 3 scenarios that we've been analyzing in our work. next slide, could you please? Also, for the 3 capacity scenarios, we've also analyzed the different operational snapshots for central continental Europe power system, and this snapshot included various operation states of the power system, including maximum load conditions. Could you click? Minimum inertia and also minimum reactive power resources for the synchronous generation in the continental Europe power system, and those parameters, those conditions have been snapped using the EDF continental model and have been provided at the national levels for the 4 different sets of countries. It includes Poland, Poland and Germany, the vicinity of Poland, and the whole Europe. So that was the 4 criterions for which these operational snapshots has been snapped. Probably you will be able to see it if you click several times on the slides, for Poland, Poland and Germany, vicinity of Poland and whole Europe. So we observed those states, operational states, for that sets of countries. So next slide, please. Also for our analysis presented within the scope of PSC Innowacje work, we have assumed that all contingencies that we are analyzing are assumed to occur in Polish power system owing to the very detailed representation of power grid model used for Poland. And if you click 2 times, we'll be able to see that for the Poland, we have a very detailed model. For the neighboring countries, we have a simplified model, and for the rest of Europe, we've used equivalent. So that's why we are in this analysis, whereas we are mostly focusing on Polish power system as it will bring us the most comprehensive results. So we can move to the next slide, please. Okay, so for the steady state analysis, we have our study brought us to conclusions that we are facing an scarcity in terms of steady state voltage regulation, which is related to the lack of reactive power resources to help power system maintain steady, safe and stable operation in terms of voltage stability. What's more important, we did not have observed any problems with the voltage regulation for the EHV network, extra high voltage network in Poland. Most of the problems that we have observed have been registered for the 110 kV network, which is quite important in Poland because it is the highest voltage level of the distribution system, and sometimes it's called as the sub-transmission system, as it is very closely related with the transmission system in Poland, especially in some less densely electrified areas in terms of the transmission system. So I think we can move to the next slide, please. So a brief summary of what we have achieved in what we have observed in task 2.4 is that, as I said, for all the scenarios, we have observed some problems with the steady state voltage regulation in terms of the lack of reactive power resources. We have observed also under voltage and over voltage problem in critical contingencies. So that's why in our scarcity mitigation analysis that I will show you in the next steps, we will be mostly focused on the distribution 110 kV network in Poland. And could you move on to the next slide, please? These are the maps presenting the spatial distribution of the results that we have observed in our analysis. So we have observed that for all the capacity scenarios, assuming more different levels of renewables, we can see the different behavior of the system. So for the energy transition, we can observe that there are some areas where we are finding some problems with under voltages. If we are moving further with the renewables penetration, going into the in the going green scenario, we can observe that those problems with under voltages are even bigger, and also they are appearing in different areas. If we move this generation, this renewable generation, towards the radial distribution system in the medium voltage, low voltage network, we can observe that some of these under voltage problems are not as visible as in the going green scenario. So there are fewer cases in the distributed renewables of under voltage problems, but still we observed several individual scenarios in which we had some problems with the convergence of the load flow, and also what it means the voltage stability of the power system. So could you move on to the next slide, please? On the other hand, we have also faced some over voltage problems, and in that case, those over voltage problems were significantly amplified in the distributed renewables scenario, because those renewables were closer to this distribution grid, in which we have faced problems with the over voltages. So we had too much generation in the 110 kV network, which led to more significant problems with the over voltages. So as you can see that in energy transition, where most of the renewables are connected to the EHV and HV network, we are facing over voltages, but they are not as harmful as in the going green, and then even further in the distributed renewables scenario. So I think we can move on to the next slide. So all those observations force us to investigate some countermeasures, how we can mitigate those problems with the reactive power, with the lack of reactive power to keep the voltages in the distribution level at the specific, at the required values. So we've proposed two types of remedial actions, remedial solutions, which include installing an additional reactive power compensation devices, such as capacitance banks and shunt reactors. And also the other proposal is to release the technically available reactive power reserves in PPMs, which are in our analysis described as an wind farms, type D wind farms, which are connected to the 110 kV nodes, because we have identified that we have, according to the grid codes, we have a very large potential of providing reactive power reserves in that sources. So moving on to the next slide.
Matthias, just 5 minutes.
Okay. So the main algorithm for our study to dimension the additional reactive power sources is to identify the critical contingencies, perform for those critical contingencies and nodes QV voltage stability analysis, find what is the stability margin for those modes, or what an amount of reactive power is needed to keep the voltages and its stability, this node stability at the specific level, and install such a shunt element that will cover this reserve. And we are performing these steps in a loop until we do not find any 110 kV node which in those identified contingencies does not meet the required voltage levels. So the next slide, please. For the reactive power reserves, activating reactive power reserves in non-synchronous wind farms, we have also proposed a similar approach, but now we are analyzing the vicinity of the problematic node, and we try to adjust the set points of the reactive power generation or the consumption of all the close wind farms in the vicinity of that problematic node, and try to mitigate those problems until we find that every problem in the grid is solved. So we repeat those calculations for each capacity and also for each operational scenario. So I think we can move on to the results. So for the installation of additional sources of renewable reactive power compensation, focused on installing shunt reactors and capacitor banks, we have observed that for the going green scenario, in general, we need less total reactive power resources needed than for the energy transition, even if we have assumed that there are more renewables connected in the going green scenario. But if we divide it into the capacitive shunts, which is capacitor banks, and reactors also, we can observe that there is slightly difference, yeah, because in going green, we need less shunt reactors because we have less over voltage problems, but we need more capacitive shunts as we are facing more under voltage problems in those scenarios. You can see that for the distributed renewables, where those renewable resources, renewable generation is closer to the distribution grid, we do not need such an amount of reactive power compensation in order to keep the voltage level in the required range. So I guess we can move on to the next slide. As you can see in those maps present the spatial distribution of needs for the shunt reactive power capacities for different capacity scenarios like energy transition, going grid, and distributed renewables. And you can see that for the areas where the under voltage problems occurred in the previous analysis, we can observe that our algorithm proposed to install the capacitor banks to mitigate those problems. Also, for the areas where we had serious problems with the over voltages, this algorithm proposed to react a shunt reactor, which helped us to mitigate those problems, and hence we have performed all those actions according to this installation of these devices. In all the critical nodes, we mitigated those problems, meeting n-1 condition in terms of steady state voltage value. Okay, next slide, please. So for this reactive power, for this issue of reactive power reserves in ppm, we can observe that, of course, we need more reactive power resources in the going green scenario than in the energy transition, as we had more problems with that scenario, and also in distributed renewables, those amount of reactive power is lower than for the energy transition and going green. That's the same reason as I presented in the static VAR devices like shunts and shunt reactors and capacitors. Even though we have
time, just conscious of time.
Okay. So I'm finishing now. So even that, we have observed that for the distributed renewables, all the problems with the voltage stability have been mitigated, except the one critical scenario that we have faced problems with the load flow convergence. But the general trend was that in the closer the reactive power reserves are to the distribution grid, the more it helps for the system, distribution system to meet the voltage requirements. So could you move on to the next slide, please? And you can see it in the map, yeah, that all the under voltage problem has been solved for the different distributed renewables. So there's nothing more to comment on that, as we are running out of time, and we can move on to the next slide. And also you can see that several problems with the over voltages also could be solved using those reactive power reserves stored in PPMs. So moving on to the discussion and to the final messages. So utilizing reactive power capability delivered by wind generation can be one of the types of voltage mitigation measures, but according to our results, there is a need to also consider additional reactive power sources like shunts or like shunts, yeah, or even some different technologies like synchronous condensers, energy storage systems, HVDC, SATCOM, or something, or even some different proposals. Also, our study was focused on the two aspects, yeah, how we can solve those problems, and this study was focused on the several aspects of the voltage stability requirements. Future work we propose that future work to complete this study could be taking into account maybe updated assumptions, because we now observe that we have a rapid growth of renewables, and maybe we need to think of some different amounts of renewable power than it was even assumed in our future scenarios, and the future is now, as we observed. Maybe some different voltage stability metrics that can be applied. As I mentioned, maybe different reactive power resources that can be considered. We also considered that maybe a multi-objective optimization of those reactive power scarcity mitigation, maybe consider of other various objectives which can be solved in the conjunction with this, like congestion management, investment costs of such a devices, and so on. Also, in the cooperation between TSO and DSO, reactive power management, we observed that it may be valuable to perform a study of coordinated TSO-DSO management in terms of solving the reactive power problems. So maybe you have some other issues that can be proposed in this discussion. So we would like to know what's your opinion on our proposals, how we can complete this presented work, or maybe you have some other proposals that you can put in comments. So okay, we are waiting for your replies, and that's everything for me. Thank you very much. I'm waiting for.
Thank you very much, Matthias. We'll move on very quickly to the poll question. So this study covers two possible solutions on how to mitigate reactive power level scarcity. In order to take into account other relevant aspects, how might the present study be expanded in the future? So your options are taking into account additional updated assumptions, updated capacity scenarios due to the rapid growth of renewables, other voltage stability metrics, etc. Considering other sources of reactive power to provide required margins. Examples: energy storage systems, synchronous condensers, HVDC, STATCOMs, static bar compensators. Multi-objective optimization of the reactive power scarcity mitigation, considering also other various objectives. Examples: congestion management and investment costs. Study on coordination, TSO-DSO management of transmission system voltage stability, or other issues to be further analyzed. So we'll give literally 10-15 seconds for this one, and we'll move on to the next presentation.
Okay, so as I can see, answers are quite equal, are quite at the level. So additional sources of reactive power needs to be considered, like STATCOM, static bar compensation, even flexibility coming from the distribution grid, yeah, from the assets connected, like energy storage systems, maybe some different assets that will be connected, like more renewables, maybe electrolyzers, which are also capable of providing some reactive power capability, yeah. And I think this multi-objective optimization also can be considered with this first topic that I have proposed. So optimization of this coordinated TSO DSO management and this considering our this analysis. And I think if you have any other question, you can put it on chat. And thank you for your attention. And I give floor to other participants. Thank you.
Thank you very much, Mateusz. Okay, we'll move on, and please do add your questions to the chat there, and our speakers will type away there to give you an answer. So we'll move on very quickly to my colleague in Airbrid, David Corcoran, who's going to present on the frequency and voltage stability mitigations and congestion management for the island of Ireland. Over to you, David.
Good morning, everyone. As John mentioned there, my name is David Corcoran. I'm a senior lead within Airbrid, and I've been involved in SysFlex Work Package 2 from nearly the get-go. So before I jump into 2.6, the task itself and the results from our work, I just want to give a very quick reminder of some of the earlier tasks within the work package and how they fed into this task itself. Do you want to just jump down to the third slide there, Christina? Thanks very much. So as you can see in the graph here, a lot of the earlier tasks feed directly into 2.6, which obviously allowed us to perform the studies. Detailed models and methodologies were developed in 2.3, and then 2.4 utilised developed scenarios and models to identify the scarcities themselves and challenges that we face in a future 2030 power system. The task showed that as we operate a power system with very high levels of res in the system, it's going to lead to certain technical scarcities or challenges on the system, and mainly due to the displacement of conventional generation portfolio. And I suppose for anyone, at the start, it's not familiar with our earlier work or termed scarcity, in this work package, we loosely define the scarcity as a shortage of something that the power system has traditionally had in good supply. So an example here probably would be inertia, for example, as it's commonly cited scarcity in high res systems worldwide. We just move on to the next slide. Thanks. So as Marianne showed earlier, due to the varying natures of the systems, particular aspects of system operation can fall into a number of categories. So obviously no scarcity, evolving scarcity, concern, and finally established scarcity. And as you can see here, the Ireland and Northern Ireland system is witnessing the impacts of the ambitious targets that we've set for 2030. And I suppose when we started off there, about 4 years ago, this target was around 70% RESI, and obviously in the last couple of months, it's been increased to a very ambitious target of 80%. But nevertheless, the key finding from task 2.4 can be summarized as the system is going to get lighter and weaker and more susceptible to events, and some of these scarcities are going to be linked. One measure may mitigate multiple scarcities, and some mitigations, while already in place, but may need to be enhanced. So if you just move on to the next slide. Thank you. So task 2.6 itself looks to establish what solutions can be used to address these scarcities. We have demonstrated via simulations and potential mitigations and the technologies that could be used to solve these challenges. However, the primary objective here was to assess the capabilities that are needed rather than focusing on the technologies themselves. So we wanted to try and remain technology neutral. And as a result, a range of system services that provide support in mitigating these scarcities, we represented them by a number of different technologies, such as synchronous condensers, StatComs, SVCs, or static variable compensators, as well as renewable technologies such as wind, solar, plus batteries and demand side. And these were all found to be suitable technologies for mitigating these scarcities, that will ultimately manifest at very high levels of renewables on the system. Now, in general, each technology or mitigation measure was largely demonstrated in isolation, so i.e. for frequency stability, voltage stability, etc. But it should be acknowledged that in reality, a range of solutions will be needed. So the mix of these solutions will be required to be assessed holistically, in order to take account of any interactions or synergies. And the reason being that some scarcities can be mitigated for a number of different technology and strategies. So the key will be to identify the right mix of technologies needed for the safety and security of the system, while also delivering value for the consumers. We just move on to the next slide. So again, as I kind of mentioned there a minute ago, the shift in generation portfolio to one with significant amounts of energy supplied by re-res or variable renewable energy sources is going to lead to greater variability and uncertainty around frequency control, mainly due to a declining system inertial response. And as we all know, rock-off or rate change of frequency due to the loss of infeed for a low inertia system is typically steep, usually causing frequency decay much faster. Task 2.4 detailed a lot of these frequency control scarcities. And as you can see from the figure here, early examinations found in the 2030 system, as SNSP levels approach 90%, the rock-offs could be quite excessive. Therefore, a mitigation measure was included within simulations where we introduced a 1 Hertz rock-off constraint into the scheduling dispatch simulations in Plexus. And there are problems with there's two ways that we can do this and satisfy this. Limit, one, by commissioning more conventional generation to increase the system kinetic energy, or two, by reducing the LSI or the largest single infeed. The task itself, established that while the naδιrs at times, were below load shedding levels, there were sufficient mitigations available. And more importantly, it showed that with high volumes of fast reserve magnitudes, in higher frequency naδιrs. So therefore, we were able to say in cases where there was insufficient fast-acting dynamic reserve capability, we saw lower nadirs, and obviously you can see that in the figure 2 of the heat map. If we move on then again to the next, so here in task 2.6, SIO or synchronous inertial response capability from synchronous condensers was demonstrated in the Irish system, as you can see in the figure here. They've been shown to be effective in slowing the rate of rock-off, resulting in a delayed nadir, thereby facilitating frequency recovery, from resources such as DSUs, pumped hydro. But it's important to note they alone can't mitigate frequency stability issues, but rather in a combination with other mitigation measures, they can be very beneficial. And they can contribute, also crucially, they can contribute to system inertia without impinging upon generational levels of, non-synchronous renewables. And more importantly, they can be quite cost effective. Also, another thing we did studies in terms of SIO was looked at, conventionals, and while the use of carbon-intensive conventional gens to provide inertia is counter to the overall objective of decarbonisation, it's probably important to acknowledge the significant role these will have to play over the coming years as we transition, to a more high-level res in the system. And we've proven, and it's also been proven here in Ireland, Northern Ireland, that with the right incentives that are in place, and if it's technically feasible, it is possible for large synchronous gens to reduce their minimum gen level, thereby enabling greater levels of renewables in the system. And crucially, that'll allow them to provide the same level of inertial response. If we just want to move on to the next slide, yeah, thank you. So FFO, or fast frequency response capability from batteries and wind, was demonstrated here in the Irish system. And you can see this in figure 1 and 2. Analysis showed that FFO provision in terms of frequency stability, especially during times of high SNSP, and it has a dual effect, so it can increase and delay the frequency nadir, obviously thereby enabling other resources with slower frequency response to contribute. Studies have also indicated that the frequency response capability in wind can be beneficial in supporting frequency stability in times of high SNSP through, POR, primary operating reserve. And frequency control wind farms in Ireland and Northern Ireland is often used to address over frequency issues. So, however, this frequency control could potentially be used to address under frequency issues. Well, obviously at times of, either when the wind is curtailed or constrained. A number of considerations for potential operation policies were also explored in addition to these services. So they include the occasional decreasing of the LSI, largest single infeed, or maintaining a minimum number of units on the system, so conventional units on the system to ensure a minimum amount of inertia. And while this is, kind of counter to what we're trying to do, these operation mitigations could be, effective in supporting the transition or evolution of the system towards decarbonisation with the arrival of system services, from non-synchronous technologies and, until they're more widespread and abundant. We just move on again, please. So in terms of voltage stability mitigation, so in the task, we demonstrate that there are many different mitigation technologies that can help, alleviate the issues observed in 2.4. So the mitigation of steady state, scarcity will require the provision of SSRP or steady state reactive power support coming from non-conventional technologies deployed in certain locations. So, from the likes of wind, capacitors, shunts, they were all shown to be good alternatives to conventional generators. Task 2.4 established the emergence of dynamic voltage scarcity during fault recovery, mainly due to the reduction of system reactive power as a result of the change in generation portfolio that I mentioned earlier. And DOR, or dynamic reactive response capabilities from synchronous condensers, STATCOMs, or SPCs, was demonstrated here. And as you can see in figure 1, synchronous condensers provide an instantaneous reactive support, while ramping, reactive support is obtained from STATCOMs and SPCs. And our results show that synchronous condensers and STATCOMs are the most suitable technologies capable of providing a DOR service here for mitigating this scarcity. If you want to just move on to the next. So analysis also showed that the fast provision of DOR is vital. Sorry, I think someone's is vital in mitigating the scarcity. So the location of the DOR resource itself is key in mitigating the scarcity. So a very important point here is that these reactive power technologies don't typically have active power, and therefore would support the overall objective of reaching high renewables and ultimately decarbonation of the power system. I suppose an additional note would be additional further studies will be required in terms, to determine the optimal placing of these resources. We move on to the next. Thanks. In terms of road triangle stability, a number of options were investigated, focusing on the potential solutions and their capabilities, including the addition of a PSS, or power system stabilizer, to the particular oscillating units, and the addition of a synchronous condenser and STATCOM to provide the needed capabilities. They were also analysed. So as you can see from the figures here, that's obviously what we've modelled. The recommendation proposed mitigation of the damping oscillation is based on reduction of the decay time, as well as reduction in peak overshoots. So the results here in the figure, we're demonstrating that the addition of PSS and STATCOM provides this significant damping, while a slightly more limited mitigation is observed for the synchronous condenser. Next slide. DOR, or dynamic reactive response capability from synchronous condensers, STATCOMs and SPCs were demonstrated for mitigating the localized synchronizing torque scarcity that was observed in 2.4. Analysis here in this task showed that large quantities of technologies will be required for this localized issue. So we conducted further studies, and it showed that the most appropriate option would be to consideration of an operation policy, whereby, under specific circumstances and system conditions, would result in a modification of a considered unit commitment itself, whereby, you dispatch down the unit that loses synchronism, while increasing obviously the output of another generator to accommodate the shortfall. And I suppose finally, the development of a new damping product, it will probably be most likely necessary in future to order and incentivize sufficient capabilities. And crucially, we've seen the system services here in Ireland have proven that they can incentivize investment in new technologies that can provide a needed capability. If we just want to move on, yeah, thank you. Look, indications across Europe suggest that transmission network congestions, may become one of the most difficult challenges in dealing with the high levels of renewables on the system. An analysis in task 2.6 showed that a number of reinforcements would be required in mitigating the congestion challenges for some critical hours. However, we also saw that further reinforcements or operational mitigations would be required for less critical hours. Results also demonstrate that reinforcements are not the only solution to the congestion issues, and alternative mitigation mechanisms may need to be considered. A preventive, security-constrained optimal power flow tool was utilised as a novel approach in our studies, in identifying optimised load shifting, gen adjustments, phase shifter angles, and tap changes. Requirements in order to eliminate congestion in the less critical hours. And the results itself indicated a combination of load shifting, optimized adjustments of the PST or phase shifting transformers would be sufficient in removing most of the overloading violations that we saw in the studies. Just want to move in. Thank you. Congestion itself, as we know, can be mitigated in a number of ways, including infrastructure investment, network reconfiguration, redispatching. However, innovative concepts such as smart flow controllers and DSM, or demand side management, was also demonstrated in this task and showed that a potential could be utilised in conjunction with other options. So from our studies, it was, we confirmed that power flow controllers alone won't be sufficient to completely remove the overloaded violations. So they'll need to be used in other conjunction with other mitigation options. And the main conclusions drawn from work on congestion management is that a range of different measures and options will be required to reduce network load while also minimising and avoiding network build. So as we transition to a power with increasing VRES, it's easy to see how congestion product increases. So the framework itself could essentially be the same for those used for frequency control, but the only difference being activation of the product is driven or triggered by congestion and with the requirement being localized. And I suppose most importantly, in order to optimize use of all these solutions, that would be required in the future, a coordinated at system level between all system players, DSO, TSO, will be paramount. You just want to move into the last slide. So finally, to ramp up, the main points from our work are Task 2.6 proposes mitigations and solutions to ensure the system can continue to operate safely and securely. The solutions, include technical options, procurement system services, and new market designs, network technologies such as synchronous condensers, STATCOMs, SBCs, as well as technologies to wind and solar plus batteries and demand side. They were found to be suitable technologies for mitigating the scarcities that we'd found in 2.4. And finally, Task 2.6 has demonstrated that renewables and non-conventional technologies are well positioned to provide this, this range of services that will be needed to mitigate these issues. And this is a critical result, as these are the mitigation measures that most likely will be available at times at very high levels of res, which we've seen, the scarcity is typically more severe due to displacement of conventional generators. Thank you. So hopefully I've left enough time for the poll.
Fantastic, David. Very interesting presentation. So we might move to the poll, but I suppose before I do is just to reiterate the importance of this work, but maybe the uniqueness as well of the All Ireland system as a synchronous area with very high levels of variable technology penetration. So it is an example of a system that has moved up that renewable capability in real time, and a system that's capable of operating up to 75% at any given time with wind on the system. So a lot of this is indicative of what would happen in other synchronous areas with very high levels of variable res. So we move on to the poll question then. So what in your opinion will be the most critical technologies capable of delivering system services to address scarcities which will arise at high levels of variable renewable generation on the European power system? And your options are network technologies such as synchronous condensers, STATCOMs, and static var compensators, renewable technologies such as wind and solar itself, grid scale batteries, demand side capability, or all of the above. We'll give it a minute. We've over 70 participants. It'd be great to get as many people participating in the poll as possible. You'll see at the top of the control bar there's an S symbol. If you click on the S, that'll bring you to Slido and the poll question. Okay, so I think there's probably a clear winner in a sense, which is all of the above. So I think it's a recognition of the need for flexibility in terms of the broadness of capability needed on the power system. So yeah, quite emphatic result there. I don't know if anybody, we do have a little bit of time for questions for David on the work that he's presented. If anybody wants to raise their hand and ask a question, or if they have a question for any of the other speakers at this point, we have a couple of minutes, so we've gained a bit of time here. Okay, maybe not. So look, we'll move on then to the next presentation. So I'd like to introduce Caroline Bono, who's from EDF, supporting balancing with new flexibilities for large share of variable res integration in Europe. So over to you, Caroline.
Thank you very much, John. Hello, everybody. Next slide, please. In this study, I'm going to start by introducing the scenarios that we have used. And so the scenarios are the base scenarios that were already, that Marianne and previous presenters talked about. So what's very important, those scenarios, is that they're based on public data. They include the targets and the directives of the European Commission. They're based on the EU reference scenarios. We have two different time horizons on the same trajectory. and they were used by all the partners. As far as the what's inside the scenarios, the core scenarios are based on an electrification of the demand for heating, for transport, and for digital. So we actually see a growth of the power consumption. We actually have scenarios that are going to include a large range of climate conditions, and this is particularly important because when we have a lot of renewables, the production is going to be depending on the weather condition. And so we want to be able to see what happens when we have cold spells, when we have episodes with no wind or little wind, and when we have heat waves. And so those scenarios are at an hourly time step so that we can actually look at a very fine time resolution if we can match the supply and the demand. And as Marianne already said, we have very large shares of renewable energies in the scenarios, and also high shares of instantaneous non-synchronous generation. So I have the same maps on the right. So you have 52% in the energy transition, 66% in renewable ambition. And if you look at the percentage of non-synchronous generation in countries like Spain or like Germany on the map on the right, you can see that the share is particularly high. And as far as what I'm going to be presenting here, I'm going to use the core scenario, in particular the one that's renewable ambition, because you have a lot of Res-E inside the scenario. And then I'm going also to work with sensitivities, because they're going to allow us to explore challenges and solutions for the power system. So next slide, please. So to explore those different solutions, we are going to look at what happens when we allow allocation of reserves on VRES. And we're also going to look at different types of flexibilities. We're going to look at interconnection, we're going to look at batteries, and we're going to be looking also as electric vehicles. And so next slide, thank you. So we use a state-of-the-art unit commitment model, and we're going to be working at the European perimeter so that we can actually see what happens with the interconnections. And the way we build our model is that we start looking country by country, and we put inside each country the power system with the different production units. We also then put the interconnection between the different countries, and then we add fuel prices, we add CO2 prices. And as mentioned a couple slides ago, we have a lot of weather uncertainties. So we have about 50 climate years to get a lot of different range, and we also have the electricity demand. And what's particularly important in there is that the electricity demand, the renewable production, and the weather patterns are all correlated. So that, for example, if it's very cold, there might not be as much wind and the demand might be high. So this is something that we actually going to see in our simulations. And then we have a unit commitment tool that allows us to have the production plan for each of the plants in our European power system. We're also going to have prices. We're going to have the interconnection usage between different countries. And so we're going to have a very, very good picture of what is happening in the European power system. Next slide, please. So this is a first graph to kind of feel why we are looking at flexibility options, at further flexibility options. So here we have an episode in Germany. So we took 2 weeks in Germany on one of the scenarios. And the slide is in 3 graphs. So the top has the generation. Then we have the cost that we see in our simulation. And the last one is the import and exports. And so on the top, you have in green the generation of wind, and in yellow, the generation of solar. And what we can see is that in this scenario, which is one that has a very high share of renewable, that was studied in the 2.5 deliverable, we actually have episodes of high res generation that are followed by episodes of low res generation, and so on and so forth. And so when we have an episode, when we have a low res generation, we're going to be having a lot of dark blue on the top graph, which corresponds net imports. So we actually have a lot of imports ensuring the demand. It represents almost half of the demand on some of the time steps. And then we're going to be having episodes where we have large res generation. So for example, like here, we have a lot of wind. And as a consequence, we are going to be exporting this production towards the neighbors of Germany in this case. And we can see that we have some curtailment because some of the production cannot be exported and cannot find a consumption in another country. And so when we look at the prices, we can see that when the generation are low, we tend to have high prices, and when the res generation is high, we tend to have lower prices. So now, on the next slide, we're going to look at the first sensitivity, which is going to see what happens when we can add reserve, or when reserves can be allocated on renewable. So we have three cases. We have a first case where the renewables are not providing any reserves, one where wind can provide reserve, and one when wind or solar can provide reserves. And so what we see on the graph on the left is that, so that's like a overall over the year, we see that when renewables can provide reserves, the reserves allocated on gas are lower, so they get reduced. And whenever we have wind and solar, since we give priority to wind, we see that wind can provide the reserves for the Spanish system. Now, if you look on the right, you have a week. On the week, you can see that you have yellow is still solar, so you have a lot of solar. And at the time where you have solar, we can see that on the bottom graph, this is the reserve allocation. So we see that when we have a lot of wind, we tend to provide reserve with green, which is wind. And this allows us to have less red, which is the gas. So we see that we have gas during the night, then we provide reserve with wind, and we can and then we don't have to have gas plants that are started just to provide reserves. So this actually allows us to have less gas production and better use of the renewables. Next slide, please. So now we're going to look at the interconnection. So we're going to have two cases. So we have the renewable ambition scenario, and we're going to see what happens if the interconnections are not as ambitious, and we have the same interconnection that in 2030. So we have the same installed capacity in both scenario of res, and then we see how much gas units are necessary to ensure that we meet the demand. And what we see is that when we have more interconnection, which is the case on the right, we need less gas units inside the European system, and this also yields lower CO2 emissions for the European power system. So this shows that interconnections are a key solution to integrate high shares of renewables. And next slide, please. So now we're going to look at different flexibility solutions. So we're going to look at batteries, stationary batteries, and we're going to look at EVs and with different smart charging strategies. So for batteries, we insert them so that they actually are inserted economically and can cover their cost. And so what we see in our simulation is that the batteries are essentially introduced in the electric peninsula, such as Spain and Italy. And And so for the smart charging option with EVs, what we are doing there is that we are actually basing ourselves on the fleet of vehicles. And so we are not having potentially the same amount of batteries in Spain, because the amount of cars that are in Spain is not the same as what we would have introduced as stationary batteries. And so in the case of smart charging with EVs, we have a lot more batteries available all over Europe because we're relying on the fleet of vehicles in all the countries. And so what we see is that when we look at how many gas plants are necessary, we see that when we have stationary batteries, we lower the amount of installed gas capacity that's in Europe. And when we use the fleet of EVs, then we're going to have a higher drop in installed gas capacities for Europe. So we have a lot less fossil fuel for those two scenarios. And so now we're going to look what happens on a week on a special example, so which is happening in Spain over the summer. And so what you can see on those graphs, so we still have the same colors as before. And so if we look at, so in this graph, you can see that you have a lot of solar production. And when we have no batteries or no smart charging, we tend to have curtailment, which is shown with the bars, like the yellow on the top with the little gray bars. And so when you introduce on the bottom the batteries, what you can see is that we actually use, we have a much better use of our solar production. And so we don't need to curtail the production as much on those particular summer week. We also, if we look at the nights of the Wednesday, we see that the amount of gas production that is needed is reduced. And globally, as I said before, the curtailment is also reduced. And so now we're going to do the same graphs, but when we have EV smart charging. So as I said earlier, on the case of Spain, which is shown around here, the installed capacity of battery is much higher, of stationary, but is much higher than the batteries that would be available through the EVs in Spain. So which is why here the EVs charging, which are in purple, are not as high as what we saw on the previous graph. And so, but what we can still see, so the top graph is the same top graph as the one on the previous slide. What we can see is that we're still seeing that we have a better use of our solar production with less curtailment on pretty much each of the day that are shown on this picture. We also reduce the gas production on, for example, the Wednesday, and globally we can see that having EVs and using the EVs with a charging strategy allows us to better use the renewable inside the system. Next slide, please. Then we looked at the market revenues for the different cases. So we have the baseline case, which is in gray, and then we actually looked at the market revenues when we add stationary batteries, when we have the two different cases of smart charging. So those are the ones in the three bars in the middle, and then we compared to the cost of those solutions, and we have the three graphs. So we have one graph for solar, one graph for onshore, and one graph for offshore on the right. And so what we can see is that adding flexibility solutions inside the system leads to an increase in market revenues for each of the renewables. Next slide, please. So Now I'm just going to summarize the finding. So by lowering the use of fossil peaking plants and lowering VRES curtailment, system adequacy is met at lower cost, better res integration in the system, and with less CO2 emissions. Interconnection represent a key solution in integrating high shares of VRES. They allow for countries to share VRES production, reduce the need for energy transfers between night and day, and reduce curtailment. They consequently reduce the need of gas-fired peaking plants. The need for gas power plants is reduced with the integration of batteries, mainly in peninsulas like Spain. Storage, either through stationary batteries or electric vehicles, helps integrating large volume of VRES in electric peninsulas, such as Spain. And VRES revenues increase with the integration of flexibility solutions. Solar revenues are benefiting from batteries integration, while EV smart charging is more favorable to wind production. And the better integration of VRES mitigates the risk on capacities and ultimately on system adequacy. Thank you very much, and I'm going to hand the floor to John and Marianne.
Thank you very much, Caroline. Another very interesting question or presentation. So we'll move to our poll questions on this particular presentation. So how do, just if you wish to click on the S button at the top of the control bar there to bring you to Slido and click on the polls. So how do interconnectors help integrate large share of renewables? They don't help, they do not help. They help reduce the installed capacity of fossil plants. They help reduce the carbon footprint at a European level, or they help reduce both the installed capacity of fossil plant or thermal plant and the carbon footprint. So if you can select your option there, see the result. So we have, again, a fairly resounding outcome there. They help, so interconnectors, how do interconnectors help integrate large share of renewables? They help reduce both the installed capacity of fossil plant and the carbon footprint. So I think it's over 90% of you have agreed with that. There's a second question, I believe, that we have that we might ask for that poll. We can move to the second question. Okay, so we actually have a question. I might just ask the question that's being presented there by Katrina Sheridan. Hi, Katrina. So Katrina just says, thanks very much for the presentation. The question is, for the batteries, what was the assumed energy for the batteries in megawatt hours?
We actually assumed the 4-hour batteries. And then the installed capacity in Spain was 25 gigawatts.
Okay, thank you for that. Okay, we'll move on to the second poll question. So which solutions can help integrating large share of renewables efficiently? So your options here are batteries, electric vehicles, interconnections, or renewables providing reserves. So what looks to be a slightly more balanced view, maybe. It's moving fairly sharply, so we'll wait for people to respond. Give it another few seconds. I'll just check for questions. Again, as I said, if you have any questions, please put them in there in the Slido question section. Okay, I think it's the poll has settled down a little bit there. So a bit of a mix here between batteries, interconnection, and renewables providing reserve, with electric vehicles maybe well behind on other options. Caroline, you might have a view on the outcome of that particular poll.
Yeah, actually, there was a fifth question, which was all of the above.
The fifth option is all of the above.
which is what my view is.
That, so we probably would have seen, I would imagine, all of the above being a fairly high contender in this, but maybe it does give an interesting perspective on electric vehicles based on the question that's presented at this point. Maybe you might have a view on that. Carla?
Yes.
Have you a view on that, the outcome?
I think that I really believe that all of the different options they each provide something different to the power system, and I think that all of the different options are very important to integrate large shares of renewables efficiently.
Absolutely, absolutely. Okay, we might move on then. I don't see any other questions, so we'll move on to, I suppose, what is the final presentation of the day. It's a summary by Marianne Evans, the technical manager for the project, on the key findings of flexibilities for the power system. So Marianne, I'll hand over to you, and then we have some concluding maybe thoughts and questions.
Thank you, John. So just to conclude this webinar, we can move to the slides. So we had seen and discussed last webinar about a whole range of scarcities that were appearing in the system and were concerning ourselves in order to move to a higher share of res, and in particular variable non-synchronous res. So what we have demonstrated in this work is that a whole range of technologies, and in particular new technologies and network technologies, have shown their capabilities to mitigate those identified scarcities, to tackle the issues of balancing variable res with by integrating in a better way the capabilities of renewables, and not only using flexible fossil plants, and provide also the required flexibilities to tackle all the issues that we have seen today associated with stability, and also to try and tackle the issue about congestions that are arising when we increase the share of variable res and distributed res in the system. So here it was just an example of some of the responses that could be provided by different technologies, for example, condensers, for example, batteries on the other one. But as we have seen, it can be provided a response, but different responses can be provided by different technologies. And what we are recommending or promoting is the fact that we will most probably need a mix of these technologies to be able to mitigate the range of scarcities that we are seeing increasing in the system. Next slide, please. So as our key findings and messages that we want to carry out is that we have here new flexibilities, new capabilities that can complete and need to complete the ones that are still provided in our scenarios by the remaining low carbon flexible plants. So we will be operating at least in 2030 a sort of hybrid system with synchronous machines and non-synchronous machines, and we need to be able to deal with that in a safe and secure way. As I was saying, a range of flexibility capabilities. Sorry, I have a box in front of my slides. Are needed to mitigate the scarcities. They were proven with some technologies. They include these technologies, but they are not limited to wind, solar, electric vehicles, as we have seen, batteries, synchronous condensers, but also different approaches. We have talked about the role of interconnections, the role also of curtailment and other flexibilities. What is very interesting and critical is that some reserves and some mitigations can be provided by the technologies that are going to be online and operating at times of high renewables. We've seen that in Caroline's presentation, but also in David's presentation. It is important that the technologies that will provide the needed responses are operating at periods of high winds, of high solar, because otherwise we will encounter other issues. So an interesting fact that I want to underline, of course, today's webinar was focused on the simulations in Work Package 2, but a big part of these responses have also been demonstrated in the project demonstration at the core of the EU-SysFlex project in Work Package 6, 7, and 8, and 9. And also proven in technology trials and QTPs that were carried out in the island of Ireland. So it is not only simulated, we also corroborated our results with actual field tests. And maybe an important point as well is that we have shown and demonstrated the capabilities, but those required responses need to be developed, implemented as soon as possible in the system, especially in particular by enhancing the system services that we ask for these capabilities to be developed and finance them, incentivize them through system services. So both technical but also economical aspects are critical if we want to see the right mix of technologies to develop and ultimately reach the net zero in 2050. So I want to point out that all the results of this work package are available on our website. You have here the link to our deliverable reports, and of course our slides and the recording of this webinar will be also available on the website. And the final slide, please. To also, I take the opportunity to tell you and remind you that this work is part of a far more complete approach and work done in the EU-SysFlex project, and that is currently being summarized in the EU-SysFlex roadmap that we will be very happy to invite you to participate in our final event on the 7th of February. And that is not only related to identifying the technical scarcities and the required flexibilities as we have discussed today, but also pointing out that financial gaps appearing in a system, in the future system, the market evolution, market design evolution that are needed to accompany this transition, the new operating tools, and in particular for the system operators. Also, when we have a little bit talked about it today, but the interest, the value of the approaches of TSO, DSO coordination, as a lot of variable generation is located in the distributed system, as well as the flexibilities, about the value as well of aggregating smaller decentralized distributed resources, and of course the essential issue of data management and all the digital aspects that the energy transition is based on. Thank you very much.
Thank you very much, Marianne. We do have a couple of minutes left, so I might just open it out to the floor. If anybody has any questions for any of our speakers, if you just raise your hand and we can, I'll ask you to ask your question. Maybe just my own question, and this is possibly for the panel, but maybe directed to Marianne in the first instance, just on the broader question of, you know, the work that was undertaken, and just to remind people that this has been a very significant body of work that's been undertaken over, you know, several years. So I would just actually just like to take this opportunity to congratulate everybody who's been involved in this fabulous piece of work. But just on a broad question of what did you find as being the most challenging aspect of this particular work package? And I'll broaden it out to work package 2 as opposed to just the mitigations. Marianne, you might have a view on that. I'm putting you on the spot.
Thank you, John. Well, first, what I found personally very interesting in this work, and as you were saying, it went on for nearly 4 years, so we have time to have a lot of discussions and chats with the various partners. Is that well, probably due to our focus of studies and our models. At EDF, we had quite a lot of work already dedicated to the issue of inertia, for example, and frequency control and containment. But it was very, very interesting for us to work with other partners who had different models and to see that there are other scarcities that we had not seen in so many details yet, and in particular the one linked to voltage stability, and that was something that was very interesting, and we had many opportunities to share our views on these scarcities and issues that are appearing in the system, and compare also our models and our sensitivities. It was also very interesting to see that in the various countries, depending on our, we have discussed the Irish roadmap for development of wind generation, for example. But it was very interesting to see that depending on our national strategies and also on the type of assets that we had in the countries, we didn't see at all the same scarcities or not in the same way. So I think that was very interesting, and at the same time, that was very challenging.
Indeed, indeed. Okay, so I don't see any further questions being presented, so we might just conclude that a few minutes early and let everybody put the kettle on and make themselves a cup of tea or a cup of coffee. As I said, finally, I'd just like to thank our presenters for a very interesting session on the conclusion of what has been a very significant body of work. I'd just like to congratulate you. Thank you very much. Thank everybody for attending, and as Marianne said, we're having our final event on the afternoon of the 7th of February, so please register for that event, the focus of which will be our roadmap. So thank you, goodbye, and enjoy your weekend.
Bye, John. Thank you.
Bye-bye.